So good afternoon. I can't be with you, but I'm going to introduce interference with you this afternoon. I'm going to speak about 10 minutes on this video, then you get these slides and you can go through it a little bit more at your own pace. So I've got the learning outcomes from SQA here, which we'll come back to. This is the inspiration as far as I'm concerned. It's to do with waves really managing to interfere with each other and give some really amazing effects. So this is the most dramatic I could think of. This is just close to where I grew up in Tynemouth. This is the North Pier on the mouth of the River Tyne in a northerly wind storm, and you can see there's a really really crashing waves where the two waves have met each other and built up to a much higher amplitude. This happens because of interference. So if the waves are in phase, where the two troughs meet together at the same time and build up a double amplitude trough, or two peaks meet together and build up a double amplitude, then that's constructive interference. So you get increased and even double amplitude from constructive interference. If the two waves arrive out of phase, where they're doing the complete opposite, then the trough meets a peak and the peak meets a trough, and both of those cancel each other out, and you end up with decreased or even zero amplitude. That's destructive interference, and it'd be worth taking a note of this in your jotter once you've got the slides yourself. So this is a recording from Porthcawl in South Wales, and you can see the two waves meeting up, and the reason that they have met up is one's reflected off the shore and it's met the oncoming wave. So they've travelled different distances in that case. And it's this path difference, as it's called, which causes most interferences. So if we take two sources, source 1, and then a second source, which has got the same frequency, it's in phase with source 1, but it's in a different location. If we do that, then the two waves take a different path of one wavelength, but they arrive in phase. So you can see that there's source 1, and by the time it arrives to the same distance as from source 2, then they're both doing the same thing at the same time, and you've got this constructive interference. In that case, the path difference must be m times lambda, where m's an integer, 1, 2, 3, 4, and that's the order number of the interference. For destructive interference, you only need a path difference of half a wavelength or any odd number of half wavelengths. So here, half a wavelength is just enough to make sure the two waves are doing the opposite thing to each other, destructive interference. 1.5 wavelengths, again, is enough to throw in an extra half wavelength to make them doing the opposite, and you end up with destructive interference. So the equation is m plus a half lambda, where m is an integer, so you've always got 1.5, 2.5, 3.5. The video that I've got for you here shows Derek Muller of Veritasium doing this with two dippers into a pond with water waves. So there's a GIF there, but I'd recommend that you watch the video from the slides where it's queued up for. So in this case, we've got an observer monitoring the wave amplitude here, and it's right down the middle between the two sources. So in this case, the two sources have done the same number of wavelengths from source 1 and source 2, so there's zero path difference, and in that case, they arrive in phase, so that's constructive interference. And you can see that in the water waves here. That's where the peaks in the ripples were much stronger in the pond. If we move up a bit across the pond here, then observing the wave amplitude here, the waves from source 1 have only travelled 3.5 wavelengths. The waves from source 2, though, have travelled the full 4 wavelengths. And in that case, because they're arriving half a wavelength path difference apart, then you've got the waves arriving out of phase, which is causing destructive interference. And seeing that on the water there, that's the area that Derek grays out in his video. And so if I overlay that, you can see that that's where you get minimum amplitude, because at any of those points there, the waves would always meet out of phase. If we move up even further, then source 1 has now travelled 4 wavelengths, but source 2 has travelled an extra wavelength by comparison of 5 wavelengths. And so there's a path difference of 1 wavelength, so they arrive in phase, and you're getting constructive interference because of that 1 wavelength path difference. Looking at that on the water, what you'll see, I've shaded it in here, is any of these points here, the waves would always be in phase, so you'd always get maximum amplitude. And overlaying that, you can see that. That's where it's brightest. So when this is seen on a GIF here with an animation, we've got right down the middle, we've got really strong, dark and bright and dark areas, and that's the central maximum where we've got zero path difference. That's all constructive interference. Either side of that, you've got the first order minimum. So at each of these points here, there's a half a wavelength path difference. So source 2 is traveling half a wavelength more than from source 1. Same thing on the other side, but this time it's source 1 that's traveled half a wavelength more than source 2. Go even further out, and this time it's the first order maximum. So source 2 has traveled 1 full wavelength more than from source 1. And the same thing on the other side, but with source 1 traveling even further. This is often shown in a diagram for an exam question with peaks and troughs shown with full lines and troughs as dotted lines. So if a peak and a peak meet two full lines, then you're going to get constructive interference. Similarly, if you've got a trough and a trough, that's also constructive interference. So you get double amplitude, but with trough. It's when you get a peak and a trough, a dotted and a full line, that you'll get destructive interference. So if I have a look at an example here, we're going from source 1 to Q, source 2 to Q. It's 6 wavelengths to Q here, 4 wavelengths to Q from source 2. So in that case, the path difference would be 6 minus 4, 2 wavelengths. It's a full number of wavelengths, so you get constructive interference. And because it's 2 wavelengths, it would be the second order maximum. If we just move across a little bit to P, S1 to P is 6 wavelengths still, but S2, source 2 to P, is 4.5 wavelengths. Take the difference between those two, you've got 1.5 wavelengths. So that's 3 half wavelengths, which is an odd number, so you get destructive interference, and that's the second order minimum. Half a wavelength would have been the first order. I'm going to ask you to have a go at this FET simulation where you can do the same thing with water waves and various other things here. And so try the sound source and the light source and do that with the just plain waves and with the double source interference there. Don't go on to the other two bits. You'll be doing that later on in the week. Okay, so that's the link for that when you get onto that there. And try different frequencies and different source separations when you do that. I've shown you this with water waves. You can do the same thing with sound. So you need to, if you're playing this, I would go into 3 minutes into the video because that's where he's actually demonstrating the sound. And same thing with microwave radiation, which has got a wavelength which is pretty convenient of 3 centimeters. And as you move this backwards and forwards here, you observe the interference being either constructive or destructive because of the path difference between the two microwave sources there. So try this example when you're looking at the slides yourself. So you've got a microwave source. It's a second order minimum, so you've got to work out what the path difference would be, and therefore you've got to try and work out the path difference there. And the second one here is with this one you've got to work out whether you would get observed as maximum or minimum amplitude, constructive or destructive, based on the two paths there and the wavelength of the source. So in summary, keywords are, in terms of phase, is something in phase or out of phase? Is there a path difference in terms of wavelengths? And using the phrases constructive and destructive. So if you have a look through the slides, and then once you've gone through them again and looked at the videos and tried the simulation, if you then go on to activity 5A from the folders.